Let us study rotational equilibrium, and we'll start studying this topic with the help of Tom and Jerry. So this is a cat whose name is Tom, and this cat is standing at a distance, let us say x t. T stands for Tom. So let us say this is xt distance from a fulcrum basically. So this is like a seesaw kind of a situation, and Tom is standing at a distance xt from the fulcrum. Now the force of gravity is acting via Tom's center of mass in the downward direction. Similarly, Mr. Jerry the mouse is standing at a distance of xj from the pivot point of the fulcrum. So this happens to be xj, and the force of gravity is acting through Jerry's center of mass in the downward direction. Alright, so essentially, if both of them are to be in equilibrium, then about this fulcrum point, the net torques have to be balanced. This is the physics principle that we are talking about, that in case of rotational equilibrium, torque net is equal to 0. If it is total equilibrium, then in such a case, force net, the torque vector and the force vector, okay, force net is going to be 0 as well. So both these conditions take place if it is total equilibrium. And if it is rotational equilibrium alone, then this condition suffices. If it is translational equilibrium alone necessarily to be holding true, then this condition suffices. Alright. If it is total equilibrium, then force net also has to be 0 and torque net also has to be 0. Currently we are analyzing the rotational equilibrium of Mr. Tom and Mr. Jerry. So let us say both of these guys are in equilibrium on the seesaw, and this is the pivot point about which they are in equilibrium. So this is the point about which we have to calculate the clockwise and the counterclockwise torque and equate the two. So the clockwise torque happens to be essentially xj into mass of Jerry into g. This happens to be the clockwise torque. The counterclockwise torque, because of Mr. Tom's weight, happens to be xt into mass of t into g. Now both these torques are going to be equal for rotational equilibrium to take place. Alright, so that is the expression that we have. Let us move on to a slightly more complicated question. So here in the diagram, this is the horizontal surface, this is the vertical surface. Now what has been given is that a rod, this slant rod of mass m, is tilted against the horizontal surface and vertical surface. So basically it is in equilibrium over here as shown in the figure, and it is kept on the horizontal surface and kept against the vertical surface. Alright, since it is a uniform rod, the gravitational force will be acting from its center. Let us say this is the center of the rod, then the gravitational force is going to act in the downward direction with respect to the center. So this is the situation. Now in this question, there is no friction on the vertical surface, mu is equal to 0, and on the horizontal surface there is friction. So the friction coefficient on the horizontal surface is mu. So let us say mu1. The friction at this point of contact necessarily should be towards the right hand side. So let us say this is F1 force, and the normal reaction over here N will be N1. The normal reaction over here will be labeled as N2. This rod is in total equilibrium. this has been mentioned that this rod is in total equilibrium. We are studying equilibrium in rotational case, and many a times when total equilibrium is given, rotational as well as translational equilibrium needs to be taken into consideration. So mg force is in the downward direction. This angle happens to be theta. This angle is given, so it is known to us at what angle the rod is inclined essentially. Alright, so if we see here, we have got three unknowns, namely n1, f1 and n2. Please understand that we cannot directly write here f1 is equal to mu1 n1. This is an incorrect equation because this point of contact is not moving. This point of contact is stationary, not moving. So we do not know whether friction will have its maximum value or not. The correct exact equation would be f1 is less than equal to mu1 n1. This will be the exact equation. Alright, now let us write down a few equations that we can write down easily. The first equation is for horizontal equilibrium. For horizontal equilibrium, we can simply write f1 minus n2 to be equal to 0. That means f1 is going to be equal to n2. So this is the equation for horizontal equilibrium. For vertical equilibrium, we have n1 minus mg to be equal to 0. Therefore, n1 is equal to mg. So these two equations we already do have, one for horizontal equilibrium and one for vertical equilibrium. Alright, we have got three unknowns. Again, I'll repeat. The unknowns are n1, n2 and f1. These are the three unknowns. Alright, now we need a third equation. So the third equation has to be the equation of rotational equilibrium. Now this happens to be the point from where two forces are passing. So it does make sense for us to be able to take the equation of torque about this point, because herein it will be the simplest possible equation, because no torque of these two forces needs to be taken because these two forces are passing through this point. So it is only required to take the torque of mg and n2. That makes things a little simple for us. This length is given to be L, the length of the rod. This length is given to be L. Alright, so we can simply write down the torque of mg to be in the clockwise direction, and mg will give a torque mg into L by 2 into cos theta. Let us see how. See, this is L by 2. Now this much is going to be L by 2 cos theta. If we consider this triangle, if we do extend this line, let us say, and if we consider this triangle, then this much amount is going to be L by 2 cos theta. So force into perpendicular distance is going to be the torque. So mg into L by 2 cos theta is the torque essentially. Okay, so this happens to be the clockwise torque. This happens to be the clockwise torque. Now this clockwise torque in total equilibrium is going to be countered by the torque because of n2. Now if we do extend n2, then we can clearly see that, let us say, if this is the extension of n2, we can clearly see that n2 into perpendicular distance, let us say this is the perpendicular distance, will give me the torque because of n2, and this perpendicular distance, this particular perpendicular distance also happens to be the same as this perpendicular distance. So this perpendicular distance is nothing but L sin theta. If we consider this triangle, then this is L and this happens to be L sin theta. So the perpendicular distance is nothing but L sine theta. Alright. Now, considering the torque because of N2 to be equal to N2 into L sine theta, we essentially get the equation. After cancelling out L, we get the equation mg upon 2 times N2 is going to be equal to tan theta. So this is the third equation that we get. From these three equations, we can find out N1, N2 and F1. So these are the three equations that are required. A very interesting situation happens if the vertical surface also has friction. Let us say if this mu were not to be 0 and if this mu were to be, let us say, mu2 for the vertical surface, then there would be a friction F2 that would also act over here. Again, we do not know whether F2 is equal to mu2 N2 or not. What we can certainly say that because of equilibrium, since it is static, F2 is going to be less than mu2 N2. This F2, all that we can say is this F2 is less than mu2 into N2. This is all that we can say for sure. Okay. Now in such a situation, you get only 3 equations but 4 unknowns. In such a situation, you will get only 3 equations but 4 unknowns. Let me analyze this situation as well. Let us say if there was a force F2 as well, then in that particular case, the equations that we have written for horizontal and vertical equilibrium would also have to be changed. The horizontal equilibrium equation will actually remain the same. The vertical one and the torque equation needs to be changed. So let us see how these equations will vary. Now F1 and N2 are cancelling each other out in horizontal equilibrium. Now in vertical equilibrium, we'll have to write N1 plus F2 will be equal to mg. This is the equation of vertical equilibrium. Please note that here we have got 4 unknowns. Like in our set of unknowns, F2 is also added. So these are our unknowns. Alright. This is a particular situation wherein we are going to fall short of equations basically. Now what does that mean in the physical world, or what is the physical interpretation of that? That also I'll mention in brief. However, this is little advanced as analysis goes, and this has to be taken with a pinch of salt. Meaning, usually questions will usually not be asked from this advanced section, or even if they do ask questions, then they will mention the certain particular value of F2 or give some extra data in order to find F2. Now let us understand what is physically happening. So these are the two equations for horizontal and vertical equilibrium respectively. Now while writing the torque equation, we have mg into L by 2 cos theta as the previously mentioned clockwise torque, and N2 into L sin theta as the previously mentioned counterclockwise torque, plus you get over here plus F2 into L cos theta. So this is the torque that needs to be added because F2 is also trying to rotate the rod in the counterclockwise sense, and F2's line of action is this, and L cos theta will be the perpendicular distance for F2's line of action. Okay, so these are the 3 equations that we have, and we do not have any other equation. So essentially F1 and F2, okay, F1 is equal to N2, this we know. Now if we do attempt to solve these equations, then unlike the earlier case, we are not going to get explicit values of every constant basically. What we would rather get, we'll see. So basically what we would rather get is a combination of 2 unknowns to be some quantity. Like for example, F1 is equal to N2 is understood and both of them are still unknowns basically. And I can write down this to be equal to N2 to be equal to F1. If I cancel out L from this equation, I get F1 sine theta plus F2 cos theta. And if I cancel, the L is cancelled out. So here I get mg by 2 cos theta. So this is what I get essentially. We cannot solve this equation entirely because these two frictions are going to self-adjust. So this is the physical interpretation. These two frictions are going to self-adjust basically, and many possible solutions are there. So on a given day, how much the friction force of surface 1 has adjusted its value to be, and how much the friction force of surface 2 has adjusted its value to be, depends basically. So this is the expression for the two frictions. So any value of the two frictions that satisfies this equation can be a solution of this answer, of this question. So this is a question which has multiple possible solutions if the vertical surface also has a coefficient of friction mu equal to mu2. Okay, so this part of analysis is slightly complicated. So even if the student is not understanding or grasping the physical reality of this part, it's okay. My intention is to only make the student completely understand the initial part wherein the vertical wall was smooth and wherein we could write down the exact equation of horizontal equilibrium, vertical equilibrium, and the single equation that contributes to the rotational torque equilibrium. Alright, let us say we move on to another situation. Herein two rods are given, and these two rods are free to rotate about this axis. This particular point is an axis. The axis is going from into the plane of paper to out of the plane of paper. So basically this axis is perpendicular to the plane of the paper. Okay. So the force of gravity will be acting in the vertically downward direction. So on this rod from the center of mass, these are two uniform rods. So on this rod from the center of mass it will be acting like so, and on this rod from the center of mass it will be acting like so. Now the length of the first rod, let us say this particular length happens to be L1, and the length of the second rod happens to be L2. So let me label the lengths. So this is L1 and this is L2. We are supposed to find out this particular angle theta. This angle theta is required. So these rods are perpendicular to each other. That is also a given fact. So this angle happens to be 90 minus theta. Alright. So since they will land up in rotational equilibrium, what we can say is this is the force mg. Okay. And this much length is going to be L1 by 2. And this perpendicular distance is going to be L1 by 2 sine theta. So the counterclockwise torque, okay, because of the rod M1, so this is M1G, alright. So the counterclockwise torque because of the rod M1 and its weight is going to be equal to M1G L1 by 2 sine theta. This is the counterclockwise torque, alright. Now if we try to analyze what the clockwise torque is, alright, the clockwise torque is going to be equal to M2G. This is the force M2G acting from the center of mass of the rod, uniform rod L2. So M2G into L2 by 2 sine of 90 minus theta. So similar analysis will hold good, but instead of theta we have sine of 90 minus theta. So this is the only single equation that we need, and ultimately we will get m1 L1 by 2 sine theta is equal to m2 L2 cos theta. So from this equation we can easily find out theta, because we are getting tan theta to be equal to m2L2 upon m1L1. So this is a simple analysis. Now let us say these are the two pulleys. One is an internal pulley, this is the internal pulley, and this is the external pulley. And let us say mass m1 is hanging from here and mass m2 is hanging from here. Since the strings are different, the tensions are going to be different. T1 and T2 are going to be the tensions, and this system is in equilibrium. Now this R1 is the radius of the outside pulley, and R2 happens to be the radius of the inner pulley. Alright. So we can clearly see that for rotational equilibrium in this particular situation, we can write down T1 R1 will have to be equal to T2 R2 simply. And for translational equilibrium in the vertical direction, we have T1 to be equal to M1G, and similarly T2 to be equal to M2G. Alright, so for this particular system, M1GR1 is going to be equal to M2GR2 as a condition for equilibrium.